morning. Let's dive right in. Hope you enjoy this little video experiment. Exercise 1 is asking us to convert a vector which is written with respect to a basis C and with respect to a basis B instead. And actually, we learned all the tools that we need to do this last time. Last time we spent some time converting vectors from a given basis. We'll call it C. It was B last time, but no biggie. Same thing. To the standard basis V, and then we also learned how to take a vector written with respect to the standard basis and write it with respect to any other basis B. So if we call this conversion process or this rewriting, if we call this rewriting 1 and that's rewriting 2, which one was easier? No, it's actually 1, because this is just doing a linear combination. This involves solving a system. That's right. 1 just involves a linear combination, and 2 involves solving a system. So this is how it's done. So with the particular example here, we have BC 2, 2. So 2, 2 with respect to C. To convert that to the standard basis, all we have to do is multiply by the matrix whose columns are the vectors in the basis C. So if we just do the multiplication real quick, 2 times 2 is 2, 2 times 2 is 4, minus 2 is 2, 1 times 2, 2 times 2, that's going to be about 6. So we have now the standard, this is V. With respect to the standard basis. Now, to convert that to the unknown coordinates with respect to basis B, we have to solve this system where, again, the matrix here is just the coordinates of the vectors in the basis B written in a matrix. So this we can do easy enough by row reduction. Adding the first row to the second row, we're going to have that, and then dividing the second row by a negative a half, we're going to have that, and then finally we can add the second row to the first row. Which means that with respect to the basis B, the coordinates are minus 2, minus 4. We can also see this geometrically.
So here's the geometric explanation. What you're seeing here are the two grids, one with respect to basis B and one with respect to basis C. Can you tell which color, the green or the purple, is the grid with respect to basis C? Okay. No, it's actually the green one. The C1 goes this way, C2 goes this way, so the green grid is the one that's drawn with respect to basis C. And as you can see here, this vector V, it has coordinates 2, 2 with respect to basis C, because we follow basis C1, basis vector C1, 2 units or 2 lengths in the positive direction. We end up here, and then 2 lengths in the C2 direction from there. So we're going 1, 2, 1, 2, and we end up right here. So V represents 2, 2 with respect to basis C. And the question, of course, is, well, what are the coordinates with respect to basis B? We already know the answer. It's negative 2, negative 4, but why? Can we see that from the graph? I think we can. So basis B1 points this way, and so the grid, actually the positive direction is this way, so the negative direction must be This way, we jump -1, -2 in the B1 direction, and then -4 in the B2 direction. Well, the B2 direction, the positive direction, is down to the left. So we need to go up and to the right to go in the negative direction. Okay, so starting over again, B1, we go -2 in the B1 direction, -1, 2, 3, 4 in the negative B2 direction, and there we are. We're right at the end of vector V. So the coordinates 2, 2 with respect to C, and -2, -4 with respect to B are the same vector.
Okay, exercise 2 is asking us to find a change of coordinates matrix. So this is going to require a little bit of analysis of what we just did here. Really, what this question is asking us for is it's asking for a matrix P that we can use to multiply the vector with respect to C, which is T2, and get, as a result, the coordinates with respect to B. So this is what we're after in this particular problem, and really all the work is already right here. This is it. So we should be able to write it down without too much trouble. Because why? Because look at what we did. We took our matrix. Let's call this matrix C, and we'll call this guy here, this one here. We'll call this matrix B. What happened? We took our 2, 2. We took our 2, 2 with respect to C. First, multiplied it by C. So this is the matrix whose columns are the basis vectors in C. And then we solved the system. So in other words, what we have here, if we write it out a little bit differently, if we write this equation a little bit differently, let's pretend we didn't do the multiplication yet. Here's what we have. We have 1 minus 1 minus 1 minus 1, x1, x2, b equals, and then instead of 2, 6, let's write this. What did we have before we multiplied? We had 2, -1, 1, 2, and then 2, 2. So it seems here that it's pretty clear how to solve for x1, x2, which we know is -2, -4, but in any case, x1, x2, we can solve for this just by multiplying both sides by the inverse. So really what we have here is x1, x2 with respect to b equals, and then we have, let me just write it in letters. So that's b, so we have b inverse. That's c, so we have b inverse c times 2, 2, c. That's it, that's our p. That's what we're looking for. P equals b inverse c. Nope. B inverse we can find again by row reduction. There's B. Whoops. We need to augment the identity matrix, and then we just go through actually exact same row operations we did before. If we add row 1 to row 2, then I guess we could do the same thing we did last time, but maybe we want to try and avoid those fractions. So let's just let's take 2 times row 1 and subtract row 2. So 2 times row 1, subtract row 2, 2 times row 1, subtract row 2. Yeah, that's going to give me the 0 I want. 2 of those minus 1 of those, that's going to be still 1. 2 of those minus 1 of those, that's going to be a -1. And then we have 0, -2, 1. And then finally we can scale both of these rows by half. And we'll get 1, 0, 0. Sorry, the first row by a half, second row by a negative a half. We'll get half, negative a half, negative a half, negative a half. There it is. That's the inverse. So that's B inverse. No, that's B inverse. And so if we multiply that by C, as prescribed over there, times C, which was 2, 1, negative 1, 2. That's 1/2 times 2, that's 1. Minus a half is going to be a half. Negative a half minus 1, that's like negative 3/2. Negative 1 minus another half, that's also negative 3/2. Then we have a half. Half minus 1, that's negative a half. So this is P. That's the conversion matrix. If we take any vector written with respect to the basis basis C, multiplied by this guy, P, we'll get the coordinates with respect to B. So it's not like we couldn't go through the more long and drawn out process we did before, but it's a little slicker. Now we just have one matrix multiplication, we're done. So we solved now for any conversion between any vector written with respect to C. Now we get the vector written with respect to B just by doing a matrix multiplication. So let's test it out. I mean, this should work, right? We take P times our 2, 2 vector. We should get where to go? Negative 2, negative 4. So let's try it. Let's just verify that this is all working out. Sorry about the racket. Hope you can see that. Let's see. So we have 1/2, negative 3/2, negative 3/2, negative 1/2 times 2, 2. Half times 2 is 1. Negative 3/2 times 2 is negative 3. Ha-ha! 1 minus 3. That's good. Negative 3/2 times 2 is negative 3. Negative 1/2 times 2 is negative 1. Negative 3 minus 1, hey! Negative 4, just as we expected. So that seems to work nicely. So exercise 3, we're asked for a change of coordinates matrix from B to C. Notice the little notation there underlined. We need to go from B to C, which is the opposite of what we did last time. So from B to C, that means we're given a vector with respect to with respect to basis B. So to convert to the standard basis, we have to multiply that guy by the matrix whose columns are the vectors in B. And let's see here. 5. So that's B. And then we have to multiply that by C inverse, which is C2, negative 2, 3, negative 7, negative 7, 10, 10, 3, 2. So inverse of this matrix. So, but before we do that, there's really, as it turns out, there's no real need to actually calculate the inverse matrix, because if we take this one step at a time, forget about these two columns here. Let's look at the first column. Multiplying this column by the inverse matrix, that's the same thing as solving this. Oh, that's a 10. This matrix equation. Which of course we can do just by augmenting. And then by the same token, forget about the first column and the third column. Multiplying the second column by the inverse matrix, that's the same thing as solving this equation. And obviously then we can say the same thing about the third column. Ignore the first two columns here for just a second. multiplying the inverse of C, or sorry, that's the inverse of, yeah, right, inverse of C times the third column. That's the same thing as solving this equation, which you can do by augmenting. So do we just do row reduction 3 times, once with each column? No. We can do better. All we have to do, really, is take our matrix C and augment all 3 at the same time. So converting from B to C is equivalent to taking C on the left, and putting B, okay, we already have it right there. Oh yeah, let's just do that. We already have it. Just erase that. Augment, and reduce. That's it. So we'll ask Sage to do that, and whatever ends up over here next to the identity matrix will be the conversion matrix P that we're looking for.
Okay, so here we're using Sage to do the row reduction in exercise 3. You see, I've just put in the augmented matrix, 2, -7, 10. So this is the C matrix here on the left, and -8, 7, -2. This is the B matrix on the right. So all we need to do is reduce. So if we just type in m dot ref, we'll get the conversion matrix, and there it is. So it's a little ugly, but that's what it is. It's this.
Moving on to exercise 4, we're given a matrix written with respect to B, and we're asked to write it with respect to C. Well, we just spent a lot of time, maybe a little bit of time in exercise 3, finding a conversion matrix. The whole point was we could just take that matrix, multiply by the given vector, and bam, we have the new vector written with respect to basis C. Again, you can use Sage to do that. Go ahead.
Okay, so now in Sage, I've just entered the matrix P, which we just found from the row reduction. I've entered it here, printed it out, that's all I have. So to convert, this is the conversion matrix from coordinate vectors with respect to B into C. So all I have to do is take this matrix, multiply by the given matrix with respect to basis B, and I'll have coordinates with respect to C. So what I need is I need my vector V, and we'll call that a matrix. That's a matrix with coordinates 2, 0, -1. And then all we have to do is multiply. So we have P times V, and that should do it. And there it is. Those are the coordinates with respect to C for the same vector. So here we're just going to double check that we understand what's going on here, and of course that our answer to the last question is correct. So what you'll see here, I put in matrix B. These are the columns. The columns of B are the vectors in basis B, and so it's printed out nicely down here. Here's a Sage code. Up here I have the Sage code for entering matrix C, and here it is down here. You'll see the columns here are exactly just the vectors from basis C. So what we know is that if we take the vector written with respect to basis B and multiply by B, we should get coordinates with respect to the standard basis. So I'm going to do that. I'm going to print B times VB. So if we do that, these are the coordinates of the vector 2, 0, -1 with respect to b. These are the coordinates with respect to the standard basis. So it's a -11, 18, -9. Okay, so if we do the same thing now, we take the vector written with respect to basis c. So this is the ugly stuff that we just got from the last calculation. That's the answer to exercise 4. If we take that vector and multiply by c, again, we should get standard, coordinates with respect to the standard basis. So what do you expect those coordinates to be? That's right. They should be exactly the same because it's the same vector, just written with the same vector as the given vector, which was written with respect to basis b. This one's just written with respect to basis c, but it's the same vector, so it has to have the exact same coordinates with respect to the standard basis. Let's see. And it does.
Finally, in exercise 5, why don't you think about it for a little bit, consult your neighbors, talk about it, maybe if Dr. Fields is still around, ask him for some advice. I'm pretty sure he won't tell you the answer, but he might give you some pointers and head you in the right direction. Maybe before you leave, you can come up with an answer.